Okay, now welcome to the fourth session of SuperMap JS training camp. Last week, we have learned the tools and skills we're going to use in vector, in the application of vector data. Today, we are going to focus on the application and analysis of raster data. So similar to the previous session, we will demonstrate the tools for raster data analysis and application and operations with a simplified JS project in reality, so that you're not only can you learn the function and usage of each of the tool, but also you can have a general you can get more familiar with the general workflow of our raster data analysis. And so here, this session is still divided into 3 parts. First of all, I will have an introduction on our study area and also on what we are concerned for this case and which goals we are going to achieve in the end. And then in the second part, we will look at data we collected for this case, and all of them are stored in a SuperMap data source, and you can find them find the data source in the materials we just shared with you. And also today we're going to use both raster and vector data sets. So we will use them to extract some useful information in raster format, and also we can learn how to generate raster data sets from vector records. And after part 2, we will have a break for 5 minutes before we proceed to our last part. So in that part, we will learn tools to reclassify, calculate, and update raster data sets, and so we can that we can integrate those independent raster data sets we have generated in part 2 together, and so that we can produce a final result for our case. So now let's first have a look on where we are going to focus on this week. So our interest is moving to the continent of South America, more precisely, southeast region of Brazil. So Brazil is the largest country in South America, as all of you may have known, and the majority of its population is concentrated in the southeast region, which is made up by 4 states. And this region also has the highest GDP in Brazil, and it's also considered as Brazil's urban and financial center. And famous cities like Rio and São Paulo are both located in this area and attracted in this region and attracted tourists from the world. However, this region is also the one mostly affected by landslides in Brazil, and that's a problem we are going to study today. So here is a simple introduction on this case. So natural hazards actually are very frequent in Brazil, and landslides are considered one of the most common hazards in this country in recent 2 decades. And in recent 2 decades, if you're concerned about, if you have looked about some news for Brazil or for the southeast region of the Brazil, then you can find that there are several severe landslides took place in this country, and especially in its southeast region. And there are research, and here we can see there are some pictures of the landslide hazard and the collapse of massive earth soil and rocks from the mountains and cliffs can destroy the buildings. And those landslide hazards with high magnitude even can be easily identified from our satellite image, like the one on the right. You can see that here are the marks made by landslide hazards. And so researchers have found out that most landslides happened in the southeast region. In the southeast region of Brazil, were triggered by heavy rainfall, and and such hazards could threaten the life of people living in those mountain areas, and also might cause huge economic loss. So it is really necessary to evacuate people from areas of high or relatively high susceptibility of landslide hazard. And so in this case, we're going to evaluate the susceptibility of landslide hazard in this specific area, the southeast region of Brazil, and our final result could be useful in landslide in the hazard management and prevention. So here, let's see what are our goals for this case. So the susceptibility of landslide is influenced by a lot of factors like the terrain, soil type, rainfall, vegetation coverage, and etc. And here we're going to evaluate 4 factors related to landslide in the study area. So their slope, annual precipitation, land cover type, and proximity to rivers. And for each of these factors, there is a criterion on whether they are whether we consider them as a susceptibility of the landslide. So we first need to get the exact value for slope, precipitation, and distance to river for the whole study area. And then we're going to determine where are those areas. And then based on those raw values, we're going to determine where are the areas that meets each of these susceptibility criteria. And finally, we will conduct an integrated assessment to combine all of those criteria together, and so with proper weights, and so that we can find the exact area of high that is really vulnerable to landslide hazard. And actually, in more sophisticated research, more factors should be taken into consideration, and the evaluation criteria and weights could be further discussed. Here we only provide you with a simplified demonstration. If you are really interested in this topic, you can go to find more research and papers and to learn more about how we're going to determine those parameters. And so now let's begin our second part. So here we will have a look on our available data set and extract factors include slope, annual precipitation, and the distance to river from our raw data sets. So here, all of our data have been stored in this data source called Brazil Southeast in this UDBX data source. And here is a simple introduction on what are those data sets is used for. So first, we have Brazil Southeast. This is the state boundary for our state boundary for our study area. And then we have a point data set, and that is the weather station in the study area. And in its attribute table, we have a column that recorded the annual precipitation recorded by each of this weather station. And then we'll have two water data sets. That is the river features in polygon format and in line format in the study area. So here, those small rivers are recorded as those line features, and for those broader or wider rivers or lakes, they're recorded as those polygon features. And then we also have two raster data sets, the DM for the study area and the land cover record for the study area. And also we have a legend file for the land cover record. So here, here, as we said before, we are concerned about 4 factors for the landslide hazard. That is slope, precipitation, proximity to river, and the land cover type. And here we can see that we already have the record for the land cover type. So here, in the second part, our task is to extract slope and distance to river, and also precipitation for the whole study area from this data set. And so now let's see how we can extract them. So first, for the slope, we can calculate from our DM data. And then for precipitation, what we really want is a precipitation surface in raster format. While here we only have the precipitation record for each of those weather station. So we need to use some raster analysis tool to produce a precipitation surface from our raw point data. And then if you want to have a further look into the distribution of precipitation values in the whole study area, we can generate a ISO region for precipitation. So these ISO regions will not be used in our final evaluation or assessment, but it can help you have a better understanding of the data we just produced. And then finally, we can use our 2 data sets for rivers to find out areas that within 5,000 meters to those rivers, and then use them for further analysis. And so now let's extract those information one by one. So first is slope. I think slope is a very commonly used concept, whether it's in our daily life or in the concept of GIS. So it is simply a description of the steepness of a terrain unit on Earth, and the higher the value is, the more steep the terrain is, and the smaller the value is, that means the terrain is flatter. So here we can see that if we use this simple DM data, then we can easily use use SuperMap iDesktopX or any other G software to produce the DM dataset for it. So now let's open SuperMap iDesktopX and to produce our first raster data. So here I have already opened SuperMap iDesktopX. If you haven't, then you can take a time to open it. And now I will show you the materials we're going to use for today. So here, the UDBX file, our data source called Brazil Southeast, is what we're going to use for now. And here we also have a reclass file. This is an index file, and we will use it later. So you just need to check if you have it. And also, here are the PDF slides for today's session. And now, if you have opened SuperMap iDesktopX, so first, as always, we need to connect our data source in our software. So select data source, and then click Open File Data Source. And here we will navigate to where we have saved our materials for the first session, and choose Brazil Southeast, click Open. And then click the button on the left, then we can see data source, we can see data sets stored in this data source. And the first one we're going to use is the DM data. We can double click to open it. So this is the DM data for our study area, and we will use it to produce to calculate the slope data, the slope for the study area. So here, among our function tabs, we need to navigate to spatial analysis. And here on the right, you can see there is a large group called raster analysis. And here, your interface may look a little different from mine because our computer have different resolutions. But as long as you can find raster analysis, then it's okay. Click on going to under raster analysis. Here you can find a group of tools called surface analysis. And under it, we need to find a group called terrain calculate. And here the first one, slope analysis, is a tool we are going to use to get our slope data set. So click on this tool. And here the source, just to check, the source data set we're going to use is DM Southeast. It's okay. And then we can set the parameters for slope calculation. Here we can see that for slope unit, we can set it to be degree, percentage, or radian. So for most of our analysis, we will calculate slope as we want our slope result to be degree. And if you are interested in slope in percentage or radian, then you can make the change. And then we need to set the name for our result data set. So here simply call it slope. And then on the bottom right, click the Run button. And now we can see that under our data source, there is a new data set produced, and that is slope data set. We can select it and drag it into our map window. Now here you can see this layer is our calculation result for slope, it's very simple and quick. So now let's go back to slides. Here, if you are confusing about where to find the tool, you can go back to our slides and to see the hint about where we have this tool and how to set its parameters. And also here, we have the result. Here are the illustrations for the DM datasets where we just used and the slope datasets we just produced. And now let's move back. Let's move to the next tool we are going to learn. So here, the interpolation analysis tool is a very commonly used tool in not only in raster analysis, but it's really commonly used in GIS project, because in reality, although we want to know some values like elevation or precipitation for the whole study area, but actually we can't have a measurement on each location in our study area. We can only have the record for some locations, and those records for these locations is called samples, can be called samples. And as long as we have enough number of samples, then we can use the sample value, to predict or estimate the values for the whole study area. And the tool used for that is here. We're going to learn is the one we're going to learn. It's called interpolation. And here on the right, you can see that how it was used. It usually take a set of vector point data set as an input, and there should be a column. There should be a column in its attribute that records the value you are interested. And then we can use this data set to calculate or estimate the surface for the whole study area. So we can know the estimated value for each of the location in this study area. And so here, when we're doing interpolation, actually there are different methods we can use, and and here is a list for them. So in SuperMap iDesktopX, generally we have provided you with 3 types of methods: inverse distance weighted, or spline, or kriging. Actually, kriging is the mostly used kriging is the most commonly used interpolation method in GIS field, as it can as it can estimate the surface value based on the spatial autocorrelation in data. And there are a lot of variations in the algorithm of kriging based on different assumptions of spatial distribution. And if you are preferred with more simplified methods, so here you can use IDW, the inverse distance weighted, or the spring line. So if we choose a spring line, it will produce us with a more smooth result that is very appealing in its appearance. And if we use IDW, then the estimated value we produced here will have the similar range as our sample values. So you can choose based on your own needs for your result. And here for this case, as we would like to produce a a more as we want to produce a result that is more visually appealing. So we will use the spline message for interpolation analysis. And so here, let's go back to our software. So as we said before, we have the weather station datasets, and now we can browse its attributes. And so here we can see that we have the name of each of this weather station and its location. And also we can see that on the last column is the annual precipitation for each of these weather stations. And so based on this column of value, we can estimate the precipitation for the whole study area and generate a surface for it. So now let's do so. Still, we need to go to the tab Spatial Analysis. And under it, still go to Raster Analysis Group. And then we can see that there is a tool group called Interpolation Analysis. And under it, we can see that here is the different methods we can choose from. We can use IDW or spline or here are three kind of kriging methods you can choose from. If you're interested in the differences between the three kriging methods, then you can simply Google it and to find some papers or articles that has a more detailed explanation on it. Here, we only wanted to know that there are a lot of methods you can choose from. And in this case, we're going to use spline and click on it. Then we can set the parameters for it. So first, we will use the weather station dataset as its input. So that's all right. Then for the fields that recorded the values we wanted, here we can change it to the annual precipitation. Like here, the one we just showed you. And so for our result data set, we don't need to change its names, but here we need to change its resolution because at the end of this demo, we would want to combine all our results. And when we want to combine raster data sets together, usually it's better to set all the raster data sets has the same resolution. So when we are producing the factors, we would set its resolution same as the resolution of our raw DM data set. And so here you can check the resolution of the DM data sets by yourself. And here I will directly tell you the resolution for that data set should be 0.00833. And then also we would want all the raster data sets have the same settings for its no value or no data. So here we will set no value as -999. Here just input minus and 49. And that's all the settings for parameters. And for the environment, here the environment settings is about the bounds of your result and also the default cell size, aka the resolution for your result. So here for the result bounds, we would specify it as it to use a specific data set bound. And here we would choose the bounds of our study area, that is the state boundaries for Southeast regions. And then for the default cell size, as we already set it in parameters, here we can set it again. And also here first choose a type to use a specified dataset resolution. And then here use the cell size of DM dataset, as we just said before. And here you can see the resolution value of this dataset. And so now that's all we need to set for this tool. And then we can click Run button. And it may take some time to produce our result. The time depends on your usage. The time it takes depends on your own computer. And as we just said before, after we produced all the factors, that is to say the slope, DM, resolution to a distance to reverse, and the land cover data, we would combine those raster data sets together. And then when combining raster data sets together, it's better that we set the resolution to be the same, so we don't have to do some further settings or changes in our data set. And here, if we click on DM datasets and check its property, here we can see under raster, we can see its resolution here. And the first dataset we just produced is slope, and it is calculated based on DM dataset. So here, if we click on slope, we can see that its resolution is the same as that of DM data. So when we are going to produce our next data sets, the interpolation surface of precipitation, we would like its resolution to be the same as the slope data set. So that's why we need to go into set its resolution. And now let's close this window first. And here we can directly add the result of interpolation into this map window. And here you can see, if I zoom out, you can see that the boundaries of this data set is different from that of slope, because it directly estimates the value of precipitation based on the bound of this raster data set. And as we all know, the bound of the data set is just a simple square or rectangular. So that's how it looks like. But if we add these boundary data sets into our map window, here, as you can see, we could clip our interpolation result based on the shape of these boundaries. And to do that, it's easy. First, you need to add these. You need to put the interpolation result and the boundary data sets in the same map window. I think most of you have done it. And then under our function tab, under the maps tab, here you can see here is a tool called operation. And under it, we have a group called map clip. And here we will choose to clip our map based on objects. And now here we can see, here is a notice that we can set multiple regions to clip the data sets in this map window. Okay, so now let's have a introduction on isolines and isoregions again. So if we are really interested about the if we want to have a clear understanding of the distribution of values on a raster surface, usually we would recommend you to create isolines or isoregions. See, so here isolines is a smooth curve. Isolines are smooth curves formed by connecting the points on the surface with the same values. And isoregions is created by closing two neighboring isolines together, so that we could have more visualization settings, like the picture on the bottom right. And so here you can see we have created isolines and isoregions for this DEM data here, and we can find that on the left part of the region there is a dense distribution of those isolines. That indicates there is rapid changes in the value of elevations in this area. And as a contrast, on the bottom middle, here is very spare isolines. Here is very spare isolines here. So that means there is little changes or a very gradually changes in the value of elevations. So with the help of the isolines and isoregions, we can quickly find where we have a rapid change. We can quickly find where we have a rapid change of values in our raster data set. And so here we're going to create isoregions for our precipitation data set here, like for this one. And so here, let's go to the tab Spatial Analysis, and under it, find raster analysis. And then we will go back to the surface analysis group, and under it, on the very top, we can see that there is a group of tool called extract isolines. And still, actually, we have a lot of tools here, like we can extract isolines with equal interval. But if you are really interested in some given values, then you can create it or extract it given values of isolines. And it's similar to the isoregions. We can create isoregions of equal intervals using the tool called extract isoregions. Or if you are specifically interested in some of the values, we can extract given values of isoregions. And that's a tool we are going to use in this case. So click on this one. So here we can see that we can specify the values we wanted to extract our isoregions. And here on the left or right, we can see that there is a tab called Batch End. If we click on it, then we can directly add a series of values here. So here first, we don't want to set the increment of our values. Here we only want to specify the classes of our values. And here we will set it to be 6. And then for the start value, we would set it to be 0 for the precipitation. and then click OK. And now we can see that here we have those values, and because we're extracting ISO regions with a given value, so we can set those values whatever we wish. So here, simply double click on the value of our second, double click on our second value, then we can change it to be 1,500. And then for the next one, it should be, oh, sorry. So let's go back to see the slides first. So here we can see that our value should start it from 0, then the next one should be 500. And so the third one should be 1,500. So here we will change the second one, the value of the second one. And that would be 500. Oh. Okay, so here we will first change. Let's have a quick review. First, we would go to click the button Batch Add. And here we would set the value, start value to be 0, and choose classes, and set there to be 6 classes. And then click OK. Now I have added some extra classes, so I would delete those if I don't want them. And here, then we will set the values for our ISO regions. So the first one should be, the first value should be 0. The second value should be 500. Then the third one should be 1,000. And the fourth one should be a while, so we can see setting those values. Okay, so we set the fourth one to be 1,500, and the fifth one to be 2,000, and the last one to be, oh, the fifth one to be 2,500. And the last one, we could set it to be larger, like 3,000. And then make sure we're creating those ISO regions for our precipitation surface that is clipped using the boundaries. And then if we want the ISO regions looks better, we need to set the coefficient parameters. So the result we produced should look smoother. So here, the resample coefficient, we would set it to be 3. And for the smoothness method, we would choose B-spline. And the smoothness, simply keep it to be 2. And you can set the name for your result data set. Like precipitation, ISO region, and then click the Run button. It will take a while. Just wait and let me see if you have other questions. And here, you can check our settings from our slides. And once you have successfully generated those ISO regions, it should look similar to this one. And you can create a semantic map, a semantic layer for this data set. So it will look better like the one showed in the slides. If you don't know how to create it, it's okay. I would show you how. Because the visualization of layers and map making is our topic for the next 2 weeks. So we will have a detailed discussion on how to create those beautiful layers and cool maps in the two sessions in the future. Okay, I'll reconnect it to my data source. And here, so because I'm only introducing you to the tool of extracting ISO regions for better visualization, and we won't use that data set for our final evaluation. So here we will just skip to our next tool in part 2, that is to create our distance raster. So here, distance raster analysis tool is the one we used to get the distance between each cells and its neighbor cells based on our source data. Like here, if we use those point data set as a source data, then we can calculate the line distance from each of those points to its neighborings and graph that's the result and so that's a result raster for our line distance. And also we can get the directions from each of those points from the location of each of from the location of each of those points to its neighborhoods, like from 0 degree to 380 degree. So that would be the direction data set result. And then we also have a distribution result. That is to say, like we have all the points in this area. And so by the distance from those points to its neighborhoods, we can see that if here, this green area is more closer to this point in the center, in the epicenter. So those area belongs, so we can say that those areas is the areas that is closest to this point. And it's also for the distribution of other points. And so here for today's case, as we are interested for the distance of rivers, excuse me, as we're interested for the distance from to rivers. So we're going to conduct the distance raster analysis. We can directly get these 3 data sets as a result, and we will only use the line distance result for our further analysis. So here, let's go to our software. And as we said before, we have 2 data sets for our river points. So first, we will select the line feature datasets for rivers, and then go to Spatial Analysis tab and find the raster analysis. Then we can see here is a group called distance raster, and here we need to find the group called distance raster, and then the tool we're going to use is generate distance raster line. And click on this tool. Now we have opened this one. And so here, the source data set we're going to use is our line feature data sets for rivers. So here we need to switch it to water L, which means water lines, river lines for the Southeast region. And here, then for the maximal distance, we would only need to find areas that within 5,000 meters to our river features. So here, first set the maximum distance to be 5,000 meters, and then the resolution for our result. As we said before, we want the resolution for all our data set to be the same as the resolution for DM and slope data set. So here we would set it to be 0.00833. And then for our result data set, as we said before, it will directly generate 3 data sets altogether, and then we will only use the first result, the line distance raster. So here, let's click the run button. Oh, sorry. I forget here, we need to set its bound. Here, go to the environmental tab. And then for our result bound, we also need to specify to use the specified dataset bound. And the bound should be that of the Brazil Southeast. And then for the cell size, set it to be the same as our DM data. And then click run. And now here we can see that we directly produced 3 data sets, and we would only use one called result street distance. And so for the other 2, we can select the other 2 data sets, and then right click, and then choose delete data set, because we don't need to use them in this case. And now this is the first distance result for our line river features. We can double click to open. It should look like this. And then we would want to also create the distance raster for our polygon river features. And so also we'll still go to the spatial analysis tab, and under raster analysis, go to distance raster and choose a tool called generate distance raster, and then click it. Okay. So if you have any questions and I have answered them, you can raise them in the chatting box again, or later I will answer them at the end of this webinar. Okay, cool. So due to the time, let's continue to our third part. So here, the third part is about our assessment procedures. First, we need to determine for each of the factor which values or which value ranges should indicate the high possibility of landslide, and where are the areas of such value. And then, as all factors are evaluated based on our criteria of high possibility of landslide, then we can combine them together to have a complete assessment. And so here there's one thing we need to notice, the importance or the influence of a factor of our factors on landslide possibility are varied. So they should be assigned different weights in the final assessment. And in this part, we will have a quick introduction first on the factor value of the factor criteria and weights designed for this case specifically. And then we will learn how to calculate and combine them together in SuperMap iDesktopX. So here you can see that is our factor criteria to say whether they are vulnerable to landslide. So for the convenience of integrated assessment, the factors are usually reclassified into a certain number of hierarchies. And here, and the number of hierarchies is usually determined based on our experts' knowledge and the discussions. And in this case, we would determine, we have determined to evaluate our factors based on 5 hierarchies. And the higher the value means the more possible, the more vulnerable the more vulnerable such area to the landslide hazard. And for each of these factors, we have the exact ranges designed for each of this hierarchy. And so this hierarchy, those hierarchies should be determined based on the local conditions. So if you are conduct the similar assessment to another area, like in Malaysia or in Philippines, then you should design your own value ranges based on the local condition of your study area. And also here are a lot of papers and researches on how to make such decisions. And if you're interested, you can learn it by yourself. And in this demo, we would use those predetermined criteria for simplification. And here, so we can see that here are the value ranges for slope, precipitation, and river distance. And we just produced our own data sets for these 3 factors. So later we would reclassify them and then evaluate and then use them for the final assessment. And then for the land cover data set, as we just said, we don't have to produce it by ourselves. We only need to reclassify them based on our criteria. So here, for the influence of land cover on the landslide hazard, areas with abundant and healthy vegetation coverage are considered has the least possibilities of landslide, while bare land and deforestation areas are very vulnerable to the hazard. So we have decided the possibility of landslide for land cover based on the criteria we just said. And here, as we all know, for raster dataset of land cover, we represent each type of land cover with a specific value. And so here you can see that some group of the values has the lowest possibility of landslide, and some of them has a high possibility of them. And here we have a index file for the land cover data set. Oh, sorry. Here we could have a quick glance on it. And so here we can see for land cover, like with the value 1 to 6 and 13, they has the least possibility for landslide hazard. And we can find from this index file, 1 to 6 is our abundant or healthy coverage, healthy tree coverage. And the 13 is very good grass coverage. And then for the group of the highest possibility for landslide hazard, here that should be the class 10, 14, and 19. So here we can see that there are bare lands and or those deforestation areas. And the other categories of land cover type has also been evaluated based on their possibilities of landslide. And you can see that which group they belong to here from this table, and you can use this index as a reference. And then after we have evaluated all the factors, our next step is to combine them together based on our assessment weights. And so as we said before, the influence of each of our factors varied, not only because of themselves, but also for different regions. And so here, the weights we designed in this case is specifically for our study area in Brazil. If you change your study area, maybe you also have to change the weights you used for the assessment calculation. And in your own project, if you want to calculate the weights for your study area, we would recommend you to use algorithms like AHP or the information content, or a combination of both to get the weights of each of the factor in your study area. And so now that's all we need to know for our criteria and the weights. Then we need to go to know how can we calculate them. So first, for our criteria evaluation, we need to reclass our raster data sets. And the tool we are going to use is called raster reclass. It's called raster reclass, and it can assign new values to each of the cell source based on our classification criteria designed by ourselves. And we can apply it to change to change the pixel value of a category or a group, or to simplify our data set, or as we did in this case, to reclassify multiple data sets based on a uniform standard. And also, in some cases, we can assign some cells as null values using these tools as well. So now let's use this tool to reclassify our factors. So first we will close those data sets. And then first we need to reclass our slope data set and select it. Then we need to go to Data tab, and under it, here is a group called Data Processing. And then in Data Processing here, we can find that under the tools for raster, there is the tool raster reclass. Just click on this one. And here we can see we're using slope as the source data set. And then we can set how to reclass it. It automatically designed a reclassification criteria for 10 classes. But here we will only reclass it to five classes. So here we can click on the range setting button here. And for the ranges, here we can change it to 5 ranges and click run. Now we only have 5 ranges, and then we can set the values for each of them. When setting them, we would recommend you to going back to our slides and referring to this table. Here we can see for slope, we need to set the values from the least vulnerable group should be value 0 to 3, and then 3 to 8, 8 to 15, 15 to 20, and more than 20. So let's go back to our software. Simply double click on the value ranges, and then you can input your own value. Here for the first range is 0 to 3. And the second one is 3 to 8. The third one is 8 to 15. Then should be 15 to 20. And then from 20 to the maximum, here we can change it to 55, so it can include the maximum value in this data set. And here, remember to check the settings for no data, and then set the name for our result. So it's the reclass result for slope. So that's how I name it. And then click Run button. Now, here you can check the reclassification result for your slope data set. If you want to say the exact value for each of the cell on this data set, then you can go to Data tab here. And under Data Processing, you can see the final group, the last group of our tool is called Raster Query. And so here, you can click on Raster Query. And once you click on it and put your mouse on your data set, you can say as your mouse moved, here are information for each of the cell. And in the last row, you can see grid value means the value of the cell where now your mouse put. And if you don't want to see it, just right click on your mouse. Now you can see it. And then our next step is to reclassify our precipitation data set. And for that one, we can see the criteria should be 0 to 5,000, 500, then 500 to 1,000, 1,000 to 1,500, 1,500 to 2,000. Sorry, here should be 2,000, and then more than 2,000. So let's go back to our software, and here select precipitation data set, and then click Raster Reclass tool, and make sure the source data set should be precipitation southeast. And then also under parameter settings, here we need to change the ranges to be 5, and click Run. And then set the ranges. That should be 0 to 500, 500 to 1,000, 1,000 to 1,500, and 1,500 to 2,000, and then 2,000 to the maximum. Here we can set the maximum to be a larger value. And still make sure you click the no data button, set the no data and unrated units to be -9999, and set the name. And then click Run. And if we added this result data set to this map window, here you can see this is how it looks like. And then our next step is to reclassify the data sets for river distance. And here we can see here is a slight difference on the value ranges for each of the criteria. For slope and precipitation, the smaller the value is, the lower the hierarchy it belongs to. But for river distance, if an area is close to a river, is closer to a river, that means it's more it has a higher possibility for landslide. So here, the smaller the value is, the higher the hierarchy it belongs to. And so when we're setting the classification criteria, we need to keep this in mind. And then here we also need to review those criteria. So within 1,500 meters to the rivers, highest possibility for landslide hazard. And then it's 2,500, 3,500, 3,500 to 4,500, and then more than 4,500. So here, let's go back to our software. So first, we would select the first data set for our river distance, and then click Raster Reclass. And here, first, we also need to change the ranges, set the ranges to 5 ranges, and click OK. And now we can see that here, it's still direct. As a default, the lower the value is, the smaller the hierarchy belongs to. And if we want to take a reverse, you don't have to change it one by one. Here is a button, inverse. simply click on it, and now you can see that the target value changed. And now the lower the value is, the higher the hierarchy belongs to, just as what we wanted. And so now we can set the values of ranges. So for the first one, with the highest hierarchy, the value should be 0 to 1,500. And for the next one, that should be 1,500 to 2,500. The next one is 2,500 to 3,500. Then 3,500 to 4,500. And the last group should be more than 4,500 meters. And here, as always, make it larger. And then give it a name. That should be river distance. Since this is for the line features, so we would mark it with L. And then click Run. Now we can see the result. That should be that should be how it looks like. And then similar, we need to reclassify that for the our second data set for our river distance created from the polygon features. So here, select the data set we're going to use, and then also change the regions to be 5. And then click inverse. Remember to do that so that the smaller the value is, the higher the hierarchy it belongs to. And then set the value range, just as what we did, before. Oops. If you have questions on the operations of these tools, you can raise them in the chatting box or Q&A, and I will answer them at this. I would answer them at the end of this session. And now let's rename our data set. And click one button. So that's how the two data sets of Raster class, so that's the result, that's a reclass result of the two data sets for river distance. And we will use another tool to combine them together later. Now, first, we need to continue our evaluation. So the last one is to reclassify our land cover data set. And maybe you have noticed that we have a lot of, although we only have 5 hierarchies here, there are a lot of categories involved in here. So now I will show you how to quickly create the evaluation criteria in such cases. So here first, select our land cover data set. Here you can find in our data source called land cover Southeast, and then open Raster class make sure here we're choosing to here and make sure here we are going to reclassify the data set of land cover, and then click on range settings. And here we will set the ranges to be 22 and click run. And here we want to change those values one by one. First, as we can see, what we did before is first we need to specify the value ranges, like from 1 to blah blah, and then in those ranges the target value should be 1. But in this case, for land cover evaluation, we can see that we directly have those varied numbers or categories that all belongs to 1, and it's hard to specify it by using value ranges. So here we would use another model in Raster array class. Here, simply in the simply on the right, you can find that we can reclassify our data set based on our ranges or based on unique values. So that's what we need to choose. Click on reclassify unique values here. And now we can see that we have 22 categories here, and we only need to specify the original values and then set the target values. And although you can set them one by one, but actually I have created a evaluation template for you, so we can directly read in that file and to get the evaluation and to get the pair of original values and target values. And to do that, we need to click on this import button here, and then we will use the XML file that is called reclass land cover. Click on it and click open. Now you can see that once we read in this file, here it has already set the original, each of these 22 original values and which categories it belongs to. And when you are doing your own project, you can set at the first time, you can set those values manually by yourself, and then you can click export and export this configuration file, and then you can reuse it whenever you want. So that's what we need to do. And here, remember, for this data set, it's no value. Here it's no value. Should be 1,255, and then give it in set the name for our result. And now add it to. So now you can see this is the reclassified result for our land cover data set. And that's all we need to do to simply reclassify our data sets based on our criteria. And you can review the settings from the slides and see how the result should look like. And now the next tool we're going to use is the algebraic operation. So that is a tool we use to perform mathematical calculations or some functional operations to our raster data sets. And here are a lot of different kinds of operations we can do, whether it's calculation or it's a condition or some conditional function, or logical or logic calculation. And so here, first, we are going to use this tool as part of our procedure to combine our two reclassified data sets of our distance to rivers. And to do that, as we want to combine them together, the combination, it's not a simply combination. First, we need to find out where the hierarchy of our distance to polygon river features is larger than that to the distance to line river features. And then we would update them, and then we would simply add those data to our river data sets. And so first we need to specify a conditional expression to find out where the hierarchy of polygon features is higher than the hierarchy of line features. And so here to do so, first, still under data tab, go to data processing. We will find a tool called algebraic operation. And here you can directly type in your operation expression if you can remember that long line. So here we would recommend you to set operation expressions, and that would open a new interface here. And then on the left, we can see all the data sets under our data source. And so here, first we need to, as we want to conduct a conditional function. So here, we first need to add a function into our expression. So here, under common functions and in other, we would choose the conditional function, and the short for that is com. And click here. So here we can see that actually we have to put in 3 parameters. The first one is a condition, and the second one is if the condition is true, what values should we assign? The third one is if the condition is wrong, what values should we assign? So here first, our condition should be if here the hierarchy of distance to polygon river features is higher than the So here we will use. So here we would determine if it's higher to the distance to the hierarchy of the distance to line river features. So double click on it to add it in. So here you can see this is the first parameters we're going to set in before the first comma. And then if the answer is yes, the value we're going to assign is 1. Just simply put in 1. And then next one is if the answer is no, then the value we need to assign should be minus 999. Just to make sure you have the same expression as I put in, as I input, and then click OK. And so now let me check if we have the same expression here. Here's also one thing we need to remember for this specific calculation. We won't ignore no data cells because if we choose ignore no data cells, we would lose some records in the polygon data sets, because in the polygon in the data sets of distance to polygon features. So here we would uncheck this one, and then we would keep the name of this result data set, and then click run. And here we can open it to see how it looks like. So here we can see all those blue areas is where the hierarchy of distance to polygon river features is higher than that to line features. And then we need to extract the values of these. We need to extract the value of these areas in the reclassified distance to polygon river features. And so, because we can see that the values in those blue lines is 1, and all the other areas is no value. So we can simply use algebraic operations to extract a river in those areas So here, still we would open algebraic operation and click set operation expression. And so here, the data set we need to use is the result data, is here, the reclassified river distance for polygon features. So click on this one, double click on this one to add it in our data sets, to add it in the expression. And then we will multiply it. We will multiply it with the result we just created here. So that's where we want to extract the value. So simply click OK. And still we need to ignore the no value cells. And then the name for this should be R river difference. And here we can see how it looks like. And so our next step is to simply update the value of these areas to our reclassified result for the line river features. And so to do that, we can copy this data set. Here, simply click copy data set here. And then for our target data sets, we will name it as R river distance. It's the same to the data set. It's the same to the original data set, but we would want to make a copy of it so that if we did anything wrong, we still have our original data set. And then we would use another tool that is data update. So data update is a tool we're going to use to update our raster data sets with another raster data set. Like the examples here, like for the first data set, we can see that it has a value for the whole interested area. And then for the second data set, it only has some new values for this area. And then if we use the second one to update the first one, then actually we directly replaced areas where we replaced the values where they overlaid with each other using the value in the second data sets. And so using this tool, we could update the values in our reclassified distance to rivers. And so here it's also under data tab, the group of data processing. And here you can see it's still under raster tools for raster data set using data update. And here, so the target data should be our original data, and that should be our river distance data set we just copied. And then we can add multiple source data sets if we wish, but here we only need one, and that is river differences, where the hierarchy of live feature of polygon features is higher than the hierarchy of live features. And so then simply click Run button. Okay. Now we'll close this one and then open this one. Now here you can see this is a combination . This is a combination of our two river data sets. And then now we can use these data sets. And then now we can use data sets we can combine our other evaluated factors together with these final data sets. But there's one thing we need to change, because when we are combining those data sets, usually we want to ignore where we set as no value. But in these data sets, we can see here, there are some areas that is far away from rivers, but still within our study areas. But they are set as no values here. As we put our mouse here, we can see. But when we conduct our combination, this is still within our study area. So they should not be regarded as no value area. So we would want to change the value of those no value areas to be 0, and that won't affect the result of our evaluation. And so to do so, first we need to open the property of this river distance. And so here we can see that its no value was set as -999. And here we would change it to be 0 and then push enter on your keyboard. And then you can click on apply. And then if we close it and reopen this data set, you can see that's the changes we have already made. So here, those blue cells, its value are still -999, but they are no longer regarded as no value data. And then we can reclassify it so that the value of these blue areas can be changed to 0 for our calculation. So here, once again, we will use raster reclass. And here for the river distance data set. And here we would set the range to be 6 and click run. Then our reclassify model or method, we would change it to unique values. And then we would set the values. Like for our original values, we would keep them at the same. Oh. Five. And then for the last one, we want to set that the value of minus 999 to be the value of 0. And you can go back to slides to see the settings here. First, we need to change the no value data for river distance first, and then we would reclassify this data set using reclassify unique value model. And here we would set, and here we won't click the no value as the no data setting, but set those unrated units as 0 as well. And then we would change the settings for the result data sets again. So if we want to, so going back here, for those unrated units, we would also set its value to be 0. And then give it a new name that should be river distance. And this is a data set we used for calculation. And then click run button. Okay, now let's open it. And here we can see that for those areas far away from rivers, but still in our study area, its value we have successfully changed its value to 0. And then we would change the no value settings for this data set to make it uniformed with our settings for other factors. So its no value should be minus 999, and click enter button, push enter button on the keyboard, and then in the bottom, click apply button. And now we can conduct our final step, that is to combine all the factors together. And the tool we're going to use is still algebraic operation. And here we need to set our operation expression. And if you have forgot our settings or our weight settings, we can go back to our slides. So here, for the assessment weights, we can see that the weights for slope is 0.5, and for precipitation and distance to river, both of them are 0.2. And then for this, for land cover, that should be 0.1. And so go back here. First, we would use our reclassified slope data set, double click on it, and then it should multiply its weight, and its weight is 0.5. And then it should add with the reclassified precipitation data set, and its weight should be multiplied with its weight, and that is 0.2. And then add with our next factor, that should be here, the distance to rivers, the data set used for calculation. Double click on it, and then multiply with its weight 0.2. And finally, for the reclassified land cover data set, it should multiply its new its weight 0.1 and then click OK. And here, remember, no value data set. And the result, we can call it assessment. And then click run. Now we can open this result. And you can see that's how the result looks like. But actually, we're only interested in the area with those areas with high or relatively high values. That should be here we can see that for this result, the maximum value is 4. So those with high or relatively high vulnerability should be between the value range from 3 to 4. And if we want to highlight those areas, we could create a Somatic Map for it. And here you can just see how I did these operations, and later we will have a further introduction on it in our future in our sessions for the next 2 weeks. So here I have made the other features, the features of other. So here I have made the areas of other values invisible. So now we can see that this is where those areas with really high or relatively high possibility of landslides, and we can overlay it with our study area features. Wait a second, maybe there's something wrong with the software. Okay, we would have further discussion on how to make this kind of maps in our next session. So if you are really interested, see you next week. And now, also, you can review all the tools we have used and parameter settings in our slides. And so now it's time for our quiz. Still, you have 6 days to complete this quiz. And if you have any questions about the tools we have used in the session, with them in the chatting box. And our next session would be on May 18th. So see you next Wednesday.